theory there's some knobs in it you can turn. But it's the only theory that when you turn the right knobs, you get that curve. All the other theories produce radically wrong results, like this. So now this data is not as good as the Planck data, but it's worth looking at. So remember, we're going this way, looking as we go from small angles to big angles. We can't avoid this fuzziness, because right here we're working at 180 degrees. They're just a limited way to sample things 180 degrees apart on one sphere, or universe. But once we get over here, we're getting the data, and this is the WMAP data. These X's, or crosses, are the WMAP data. And Planck sits right on top of the data. This red curve is the prediction of Guth's inflationary theory. But we have some others here. For a long time, there was this idea of something called cosmic strings, sort of a structure in the distribution of galaxies that doesn't take into account what was going on in the early universe. It's sort of a geometric model of what can happen, and it's dramatically wrong. It gets this bump right, but the rest of it doesn't notice these. Now, what are those bumps? Those are the sound waves in the early universe. Once the universe became transparent, the sound waves propagating in this super dense plasma that existed until 380,000 years, once the universe became transparent, that distribution of bumpiness was frozen in. And it has not changed since. It got bigger because the universe expanded. But these are the bumps from acoustics in the early universe. There's others here. And so this model is called inflation. Here's a model of inflation without dark energy. I've mentioned dark energy a number of times in the first two lectures. If you say, I don't believe in dark energy being a factor in expanding the universe, you can believe that, and you get bumpiness, you get this first echo, but then the rest of it just doesn't match. Here's the open universe, the one that looks like a saddle. No, that doesn't look right. Bumpiness, but in the wrong places. And this one, the red line, is inflation with dark energy. It looks right. There's still people arguing about it, but it looks right. Shall we take a break? I know we started a little late, and if you're willing, we'll go a little late to make up for it. Now I gotta go babysit the camera. Welcome.
Sorry I was late. I had a concert today at the barber shop.
Were you performing?
Yeah. A little luncheon thing.
Nice. What's your baritone? Bass.
I'm singing lead nowadays.
Oh.
You sing?
No, I'm a piano player.
Oh, okay.
I'm a piano student.
We're always looking for somebody to come sing with us.
I got someone. You'd have to convince my grandson, who is a very experienced high school choir singer, and he's into the singing. As I say, he's in high school. His brother goes to school here, and is a young man who's not going to go to a college that doesn't have a singing program.
Amazing. We sing down at Christian Church in Loveland. Tuesdays at 7
I was
o'clock.
just in Loveland this morning. You missed me talking about my day. I have a consulting job with NASA, and it involves being on the phone a lot. And I had, from 8 to 9, I have a consulting phone call, and then from 9 to 1. But I have to be looking at a computer screen when I'm doing the consulting stuff. So I realized I can't be in my car driving between 8 and 1. So I had to be here at 8 o'clock. They gave me a nice little study room, and I was on the phone for 5 hours.
Yeah, you've had as busy a day as I have. I got out of my tux shirt before I came here too.
Oh, wow. You got a busy day. We have news. I think I'll announce the news. Since it's going to be fun. There's no reason I can't announce it. I think it'll be impressed. Well, not impressed, but
For you.
for me, yes. Yeah, it's good news.
Good.
Now,
Age of the Universe.
yes, here's why there's an issue, and we'll talk about this one.
I'm just, you know, I kind of read it, I didn't quite understand why, but,
We're going to talk about it in a future lecture, but I will, when the group reconvenes here in a few minutes, let's talk about this. There is a serious problem with, that has just emerged in the last, let's say, 2 years. 2 different techniques for measuring the age of the universe, and they disagree substantially.
2 billion.
About, yeah. That's why people are, and the problem is, let's see, it's not in this lecture, but the most recent Nobel Prize for cosmology, astrophysics, was about how do we measure the age of the universe, and everybody said, oh, those guys did it right. Yeah, come to Stockholm and get your prize.
That's the Hubble concert.
Yeah.
So they want their money back?
I was in Stockholm this year, actually. We went on a cruise from Copenhagen around the Baltic, St. Petersburg, and Stockholm. And one of the stops we made, the guide was saying, you see that restaurant over there? They do the Nobel Prize dinner, and they keep the menus. So if you want to, like, if you want to have the dinner they had when Richard Feynman got his Nobel Prize, it's like $550 a person.
Oh, good God.
It's not cheap, but they will serve you the same spectacular meal. But let's age of the universe.
Yeah, I'm just,
Let's bring that to the attention of the other
above
students.
my fingers.
This is a major problem. Yes, we have recording.
This is the first lecture from Cosmic to that three that was out there. What is it?
When we get done, if you, because you're the only one that's not here, you and I can have a private conversation. Now, I asked some people about getting lecture one downloaded.
Yeah.
And they're not having a problem. So
Oh,
do it again.
operator.
Do it again. And what I've done is, actually, let me talk to the whole class about this. I think we have most everybody. So we have a couple of things to talk about. First of all, let's do a little administrative thing about the lectures that are on the website. What I've done is I removed the PowerPoint files. When if you've been in class and you look at the slides, you don't need the animations. So what you have there are the PDF files, and everybody should have, probably by now, everybody's got a PDF reader like Acrobat. And those are much smaller files, so they should be easier to download and faster. So has anybody, the gentleman, Marv, has had an issue with downloading the first lecture? Anybody else problem with it? So Marv, give it a try.
I get a warning that says that it can't check for bugs in it, but other
Oh, that's all right.
but that's no problem.
Can't scan.
You know, if you
Yeah.
just say okay, it'll download.
Yeah.
Fine.
So as far as I know, we are bug-free.
Yeah, I don't.
So now, let's address another topic.
Are you going to post the PowerPoints all of that?
If you want the PowerPoint, write to me and I'll find a way to get it to you. But for a lot of people, the PowerPoint will offend your browser, because one of them is 225 megabytes. But you know, visually they're the same. The only thing you'd be missing when you use PDF is the animations.
In the PowerPoints, you can select all of these different images and capture them, steal them from you, and paste them.
You can do that with PDF.
Yeah, but you don't get the original.
You don't. So if there are images that you want, okay, let's cover this too. if there are images you want, write to me and I will give you a link to the images. Because many of my images came from, not this one, but many of them come from a textbook I used to teach astronomy a couple of years ago, and from Google, so forth. Now, a question's been raised about another topic, and that is we will talk about more, but I want to keep you current on what's going on. It has to do with our measure of the age of the universe. So Hubble, we already talked about the history of this. Hubble was the first to notice galaxies going away from us and calculating the rate and discovering that the farthest galaxies are going the fastest. And so it implied expansion of the universe. And that number, that measurement has been made thousands of times by graduate students over and over again. It's one of the standard things that astronomers tell their students to do. Right now there's a real conundrum about the age of the universe because multiple methods, this is true in all of science, multiple methods should give you the same results. And there are two groups that are prominent in measuring the age of the universe. One of them relies on the shape of these bumps in the cosmic microwave background, and they get a number. And there's another group that uses supernova events, and get a different number. And the numbers are about 10% apart. No, not 10, 5. But it's, nobody thinks this. The two numbers, doesn't matter what the units are. I think the supernova guys get that, and the CMB, when I say CMB, I'm talking about that cosmic microwave background. They get 72, maybe? Way too big. Oh, and this is a number that relates to Hubble's constant, which talks about and describes the expansion rate of the universe. But it turns out, it's very interesting, Hubble's constant, if you turn it upside down and do a little arithmetic, this is the age of the universe. The reciprocal of Hubble's constant is the age of the universe. So you can see, let's take 70 as an example. Kind of the average here. If you take 1 over 70, let's just figure out roughly what we're talking about. 1 over 7 is about 1.3. If you do the units right, you don't get 1.3, you get 13. So the reciprocal of Hubble's constant turns into the age of the universe. So if the universe is expanding faster, it's younger. And what we're seeing now is a difference here in the Hubble constant measurements, and it implies a difference in the age of the universe that is intolerable. And people are scrambling. And I was saying to a group earlier during this break, there's a group of guys, most recent group to win the Nobel Prize in topics related to astrophysics, Alan Rice and his group, they just won about 6 years ago for making the most accurate measurements of Hubble's constant. They might have to give the money back. So, but let's go back to this amazing piece of art. So, just to reiterate, there's a lot of different models for the evolution of the universe. The only one that gets anywhere close to working is Guth's inflation model, which is a revolutionary idea about what happened in the first billionth of a second in the universe. And it's captured in the drawings. A lot of times the drawings don't talk about it. So let's go backwards here and I'll show you. Oh, there it is. Right here. It's captured in the drawings in a kind of quiet way. There's the word inflation. And what we're talking about is the universe starts out as a thing smaller than an atom and immediately got gigantic. It grew in a fractions of a second by a factor of 10 to the 69th. Just, and it solved all sorts of problems. Now I give these lectures a lot, so I don't know, did I talk about the flatness problem? Is that something I mentioned yet? Maybe not? Did?
That was introductory.
Oh yeah, I might have just brushed over it. Guth's model solves the flatness problem, it solves the monopole problem, and it solves the horizon problem. And my high schools, I volunteer at a high school down near Boulder, and the elite math students in high school can do the math that Alan Guth did. I have to show them what to do, but they can do the math and get this result. Later in the year, I'm going to go to Chicago for part of my consulting for NASA, and my friend pointed out to me that the Museum of Industry and Science, is that what it's called in Chicago? Science and Industry, down in the basement, in a hidden spot, you have to know where to look. They have Alan Guth's notebook, where he's writing in handwriting, speculating about what he could do to try to explain away these problems in cosmology of the early universe. And then I'm going to go take a picture of this when I'm in Chicago in December. It's got like eureka. I know what happened. This thing happened, and we do this math, and we get the result. So I told my friend Hugh Davis that I have interesting news related to this, sort of related to this class. I'm a registered speaker for cruise ships. I've been registered with them for 2 years. They never call me. Today is Thursday. Tuesday night, they sent me a note and they said, we have an assignment for you. From Dubai to Mumbai, India, in December, right after I go to Chicago, for 11 days, to lecture on astronomy and these topics that you guys have helped me make better because of your very thoughtful questions. So my wife and I are going to go to a place in the world we never considered going. And during that cruise, there will be an eclipse. And the boat is going to go sit in the middle of the totality of the eclipse. So we will not be available at the end of December.
Let's hope we're not at war.
Yes, thank you, Helen. Thank you for that.
Positive state.
Yes. All right, so you see where we are here. The Planck. Oh, and now, so we can go back to this drawing. I remember I said a couple times the first time I showed this that we drew a very nice blue line through all the dots. A statistician did not do that. This is Guth's model. Now, he has some numbers he has to put in, but that's okay, because this is the only model that works. And it explains some results that were otherwise unexplainable, and it matches the acoustic peaks. So if you go to, next time you're at a dinner with friends and they start talking about what are we doing out there, and why are we doing this? And it's because we now understand the acoustic spectrum of the early universe. So once again, this is drawn to try to represent what goes on with inflation. So we have something happened here, we don't know what, and we have this explosive increase in the size of the universe. And this, depending on how you interpret what Guth did, this happened before the so-called Big Bang. If you describe the Big Bang as the interval of time during which the first particles formed, which later became atoms, this inflation event happened first. So the Big Bang is not the first thing that happened in the universe. there was this nugget of quantum fluctuation, something, and we have inflation, and then we have creation of the particles that ultimately became the atoms. And when atoms formed, then we get, here's the cosmic microwave background, because at that time, the universe became transparent. And then you see the dark age, and then astronomy starts. So that's a nice drawing to sit and think about. Now, yes, sir?
That figure shows the inflation of the universe, and it's not much bigger, according to that, looking at that figure today, as it was after it expanded. So,
Right.
I mean, what is the difference in what was...
Well, the universe has expanded. The fastest receding horizon that we experience is leaving us at about the speed of light. So the universe got big immediately. Remember, I wrote this number down. Now remember, it started out, it was unbelievably tiny. It was probably the Planck scale, and the Planck scale is 10 to the minus 32 meters. So if you multiply, if you say I started with something that small and increase it by this, we're up here in the 10 to the 40th meters, and that's about the size of the universe today. It's bigger now. But the biggest, it's like talking about a baby, the interval during which a human grows the most is the first year. If you include impregnation, you're starting with a little nothing, and a year later you got something that weighs, I don't know what a 1-year-old weighs, 25 pounds.
So,
So if we started at 10 to the minus 32, got to 10 to the 69, where were we after the Big Bang?
Oh, the Big Bang takes us from 10 to the minus 32 to something on an atomic scale.
Okay.
So, nanometers, 10 to the 9th, 10 to the minus 9. Sorry, I ran out of space here. I'm trying to do these in order. So, well, bigger than an atom.
Okay.
And then there's all this debris. And Marv has asked me, maybe I'll do a summary again for Marv, who could not be here for the first lecture. That period between the beginning and the formation of the first atoms, the energy levels were so high that parts of what we would now say are subatomic particles, like electrons and protons and neutrons, they couldn't exist. If they started to form, they'd be immediately shattered by high energy radiation. And I mean shattered down to the smallest pieces of stuff that we imagine exist. So when you get the first lecture, there's a lot of stuff in there about that. Now, yeah, we can look here. So I told you, we now understand the acoustics of the early universe. These peaks represent sound waves banging back and forth in an expanding universe. But there's something else we get out of this. The relative height of these peaks tells us how much of the universe is us stuff, atoms. How much is not atoms, is energy that we don't interact with. And how much of it is matter that's not like us, so-called dark matter. So let me show you the result of that. And it comes right from the height of these peaks. And there it is. This is important too. So dark energy, we now know, the universe, you take all the energy in all its forms, so roughly 70% is called dark energy. And it has some very interesting properties. 27% is dark matter. It's stuff we don't interact with. It doesn't interact with light, but it has gravitational properties, so it influences the way galaxies evolve. Everything that we are made of, and stars, and galaxies, and potatoes, are all in this little 5% wedge.